Alright class, let's dive into the topic of energy and power in a wave. And the first thing you must take head on is the confusion that if in a transverse wave the particles of the string move up and down only, then how does the energy move forward? Well, I want you to imagine the string as a series of tiny segments connected by tension. And when you pull one segment up, the tension in that segment pulls on its neighbor. And because the string is sloped, that tension force has a vertical component that does work on the next segment. And in physics, doing work is just a technical way of saying transferring energy. Therefore, as one piece of the string moves, it does work on the next piece, which does work on the next, and so on. And you could say this is the relay race of energy transport. But where is the energy? To understand that, imagine a very small string element of mass delta m and length delta x oscillating transversely in simple harmonic motion as the wave passes through it. And listen to this point carefully. As the string element oscillates transversely, its length must increase and decrease in a periodic way to fit that sinusoidal waveform. And just like a spring, there is elastic potential energy associated with these length changes. So let's look at a snapshot of a wave. You might think the most energy is at the peak because it's the farthest from equilibrium. But it's actually the opposite. At the peak, that is y is equal to a, for a split second, that piece of string is at rest, that is its velocity is 0, which makes a kinetic energy 0. It's also at its normal length, that is, it is not stretched, so its elastic potential energy is 0 as well. That is, at the peak, the instantaneous energy density is minimum because both the transverse velocity and the local stretching are 0 at that instant. At the equilibrium, that is y is equal to 0, the string is moving the fastest, meaning maximum kinetic energy. It's also where the string is most stretched and slanted, meaning maximum elastic potential energy. Now, let me bring up this important point here. That is, do not confuse this with simple pendulum or a standing wave where the energy swaps back and forth. In a traveling wave, the energy travels together in a packet. That is, the wave effectively transports these packets of high energy down the string at the wave speed v. And if there is one thing you must memorize, it's this. The energy of a mechanical wave is proportional to the square of its amplitude. Think back to the simple harmonic motion. We know the energy of an oscillator is E is equal to ½Ka². Since every piece of a string is basically a tiny harmonic oscillator, it follows that same rule. If you double the amplitude, the wave carries 4 times the energy. If you triple the amplitude, you're looking at 9 times the energy. Next up is power. That is defined like always as the rate at which work is done or energy is transferred. For waves, the average power depends on 2 things. 1, the medium. This includes the linear mass density mu and the tension of the string. And these factors determine the wave speed v. Therefore, for a given amplitude and frequency, a string with larger mu or higher tension transmits more power. And 2, the source. This is u. Now, we know that the energy in each individual pulse depends on the amplitude A². But you don't just care about how much energy is in one pulse. You care about how fast you are pumping that energy into the string. That is power. Think of this way. Amplitude is how big each energy packet is. frequency is more oscillations per second and larger transverse speeds of the string elements. And here is the kicker that often trips up students on the exam. For a given medium, the source has two ways to ramp up the power. If you double the frequency while keeping the amplitude constant, you aren't just working twice as hard, you're pumping energy into that string 4 times faster. And likewise for amplitude, that is, if you double amplitude, the energy quadruples. But what if you double both? You've just increased your power output by a factor of 16. That's why high frequency, high amplitude waves are so much more expensive for the source to create. That is, the source requires a lot more energy to get this kind of multiplier effect. Okay, having understood the concept, let's get into the math and look at the rate at which this energy is transmitted. And for this, we start with the kinetic energy dk associated with a string element of mass dm, which is given by dk is equal to half dmu². And here u is the transverse speed of the oscillating string element. And to find u, we need to differentiate our wave function with respect to time while holding x constant. That gives us u is equal to minus omega a cos kx minus omega t. Then using this relation and substituting dm is equal to mu dx, we can rewrite our kinetic energy equation as dk is equal to half mu dx minus omega a square cos square kx minus omega t. Now, if we divide both sides by dt, what we get is the rate at which kinetic energy passes through a string element. Notice, since dx upon dt is simply the wave speed v, we arrive at dk upon dt is equal to half mu v omega square a square cos square kx minus omega t. But you know that dk upon dt represents the instantaneous power and therefore varies across the oscillation cycle. And this variation is mainly because of the cos square term that makes it pulsing rather than constant. It hits a maximum when the string segment is at the equilibrium position, where the cos square value is 0, and drops to 0 when the segment is at the peak, where the cos square value is 0. Therefore, to find the average rate at which kinetic energy is transported, we take a look at one full cycle of the wave. And the math tells us that the average value of a squared cosine function over a full cycle is half. That gives us dk upon dt average is equal to 1/4 mu v omega square a square. Now, we also have to account for the elastic potential energy. While we won't go through the full proof here, you should recall that in oscillating systems like this, the average kinetic energy and the average potential energy are equal. That is, dk upon dt average equals du upon dt average, which is nothing but 1/4 mu v omega square a square. So the average power, which is the average rate at which both kinds of energy are transmitted by the wave, is simply the double of the average kinetic energy rate, or P average is equal to 2 times dk upon dt average, which leaves us with this final very important result. P average is equal to half mu omega square a square. And notice that the factor mu and v depends on the material and tension of the string, while omega and a depend on whatever process is generating the wave. And this dependence of the average power on the square of the amplitude and the square of angular frequency is a general result that is true for waves of all types.